Thank you, Joseph. Hello, everybody. Today, I'm going to talk about machine learning in structural design. If you have some questions, please let me know. We will try to make this presentation as didactic as possible. My name is Bruno Ribeiro. I am a PhD student in a project between Brown University and Delft University of Technology. My supervisor is Miguel Bessa, and I am also a research intern at Inductive Research Labs. It's a scientific machine learning. I am studying how we can apply machine learning techniques to help solving challenge in mechanical engineering, especially in looking into neural methods to solve partial difference equations. And if after this presentation you have any questions that you would like to discuss in more detail, please send me an email or a message on LinkedIn. The work that I will present today was developed together with João Ribeiro, also a PhD student, who will tomorrow present a workshop about our work. This presentation will be divided into 4 main parts: introduction to machine learning in structural design, the problem under study, in this case, plate with the holes, the data set that we developed, SimuStruct, and then I will move on to the machine learning methods. I will start and I will focus more in the simple one, multi-layer perceptron, but I will give some ideas and some results that we already did in the past about convolutional neural networks, and recently graph neural networks, because now we are focused on use graphs, neural networks, and use the data that we already create. Okay, so numerical simulations are used to solve real problems in many domains, such as fluid dynamics or structural mechanical. However, numerical simulations such as FEM are often slow and computationally expensive. Furthermore, the design process is iteratively and demands a rerun of the simulation each time a parameter is changed. This can end up very quickly both in time and computational resource. So in this case, machine learning can be a very impactful tool to reduce the time needed for the development cycle. This work introduced the simulated structural part dataset, SimuStruct. The dataset contains plate with the holes. The first question is, okay, so why plate with the holes? The main purpose to start with the SimuStruct dataset of the plate with the holes is due to be the simplicity of to these problems, which for different cases we can easily verify by analytical expressions. And in addition, it is a classic case of mechanical engineering, which can be found in various applications. I put here some pictures from our day-to-day, such as construction of buildings in the aeronautical industry, or even in the biomedical applications, among many other applications. This set of applications makes the problem interesting, enabling the development of new approach for mechanical systems design. Furthermore, with the population of MEL techniques to address mechanical engineering problems, a significant potential impact enabling the design and development of more sustainable systems and with less effort and time. Now, I will introduce the data set and all the steps that we did from the first until the end to receive the data. We call SimuStruct, and SimuStruct is composed by many geometric cases of the plate with the holes, with different loading conditions, diverse types of boundary conditions, and different materials. If we combine them, a significant library enabling fast analysis of multi-problems and optimizations proceeds in mechanical design tasks. This dataset is obtained through standard FEM using scripting for automation, the model generation. In this case, we use Phoenix, is adopted. Science is an open source library, so everyone can have access, and so it could be more easier for all the people use it. And the scripting also consider different levels of refinement of the mesh, aiming to evaluate the mesh influence in the outputs. SimuStruct aims to serve both as training and evaluation data for ML-based methods for computational stress-strain fields and optimal mesh definition, and therefore support the development of ML-based optimal mechanical design solution. In addition, the dataset is intended to be used in academia and industry, contributing to the connection of mechanical engineering and MEL community, which will accelerate the research in computational mechanical design. Now, I will speak about the methodology, all the steps to generate and process the dataset are described. So first, we need to define the geometric case. And for that, we use the book that I put on the right. And with this book, we separate the different types of geometric case included in this dataset, as it is a reference in mechanical engineering community and contains many different cases, giving diversity to our dataset. Geometric cases are defined by presenting a rectangular plate with the holes, and we can change the shapes of the holes, such as circular, rectangular, or elliptical holes. The different types of geometric case implemented in this dataset are 7. So we have like one single hole, 2 holes, row of holes, double row of holes, and you have some patterns. And because we have 3 types of shapes of the holes, so we have in general 21 different geometric cases. After defining the geometric case, we need to define the mesh, and we have different mesh that we create using Phoenix. The mesh are constituted by regular triangular elements, but we can change the density of the mesh. So we have a parameter, and we can decide the density of our mesh. Several mesh were created by each geometric case for different levels of refinement to make a study regarding the mesh resolution and the mesh sensitivity to the output results. The mesh types can be divided into 2 groups because we have like the mesh and we don't make any refinement around the holes, and we can make the refinement around the holes. And for each group, 3 levels of refinement were made, and all these mesh are written in XML extension files. The plate will have on a single material, being isotropic and linear elastic, and it is necessary to indicate the material properties, like as Young's models and Poisson ratios, to characterize the material. We have like for steel, aluminum, but of course we can add the material that you want. For the loading conditions, 6 types of loading conditions were defined, as we can observe in this figure, like uniaxial tension, biaxial tension, pure shear, simple shear. So we have 6 types of loading conditions. And regarding the boundary conditions, a certain boundary of the plate could be free, simple support, or clamped. So taking in account these 3 cases, 6 types of boundary conditions were defined for the plate. For example, for case A, all the edge of our plate are free. So we define FFF. This case, 2 are free and 2 are clamped. So the code is like CF. And for other examples, we need to use the same knowledge. The numerical model can be created using a mesh, materials, loading conditions, and boundary conditions. Note that the model creation corresponds to the FEM pre-processing step. After the model was created, it was solved using Phoenix, and the results that we obtain for each of the models created are the displacement, the stress, the strain, volume stress, mass geometry, and mesh topology. Note that the results are saved in image, namely PNG format, but also in numerical formats using CSV files. With these 2 different types of data, it can be employed different MEL models, such as MLP, CNN, GNN, which increase the number of SimuStruct dataset applications.
Just real quick, Bruno, this is Walid again, asking some basic questions. So you're saying you want to use a network to solve, you said earlier, to solve these partial differential equations. So you're going to present the network with what are you going to present the network with such that and then what is it going to give you as its output? Could you just summarize that? So you're going to present the network with something, and then it would have been pre-trained using your sample data set. Just one more time, what is it going to generate at the end, and what is it going to be presented with?
Yes, I will talk later about it, but the idea today is like to try to predict the volume stress, using our data set. So we don't need to use the FEM because you have a lot of data, so you just need to train MLP, and with that we can predict the volume stress for a different case that we don't train in our neural network.
Okay, and that stress is a set of parameters, or is it one number?
Is only one number, because the volume stress you can use it for each node on your mesh. So
it's for each node on the mesh.
Yeah, for each node. Okay. We'll predict that. Yeah.
Okay, and then it's okay, got it. Okay, thank you. Sorry.
Okay, no problem, bro. If someone have more questions, please make the questions, and later I will talk about that. And so if you still have some confusion or some ideas, please ask me again. So about the application, now I will present the applications for the dataset. The case that we are studying is a plate with the holes. In this case is under biaxial loading. There are compressive loads on one part of the edge and traction loads on the other part of the edge. It is a thin plate under plane stress. The material is linear elastic, undergoing small deformations. So this presentation will focus more on MLP, where I will describe the entire process developed from splitting the dataset, building the model, and making the predictions. Okay, so what is the goal? Our present goal is to try to predict the volume stress at any point in the plate. In our study case, the boundary and the loading conditions remain constant, as well the material properties. So only the geometry of the plate will influence the stress. The inputs used are two, the point where we wish to evaluate the stress and the plate geometry. So the question now is, how could we pass the geometry information to our neural network? Initially, we thought of using a regular mesh of points. The regular mesh has the advantage of having a fixed number of points, regardless of the geometry of the plate. And one of the inputs is an array with the coordinates of the points of that regular mesh. But since the stress is higher in the regions near the holes, we call stress concentration, it is more advantageous to have more points in that regions. So we create an unstructured mesh refined in those regions. Seems like the best solution. The disadvantage is that the number of the mesh points is no longer fixed, so will depend on the geometry of the plate. So we have two inputs. One of these inputs is an array containing the coordinates x and y of the given mesh point, and the other inputs referring to the geometry of the plate will be three components array. The first is the coordinate x for the center of the hole. The second is the coordinate y for the center of the hole. And the last one is the radius of the hole. So the inputs have shapes 1 by 2, the first one, and the second one have the number of holes by 3. And what put is a simple value, one value, that is volume stress at this point of the mesh. That data set was generated using the SimuStruct, being constituted by 1005 geometric cases. That data set is divided into training and test, but now we need to guarantee that the training and the test data are significantly different, allowing to test the validity of our model to generalizer to unseen case. It is necessary to follow the 3 steps. So we need to evaluate the similarity of the data, group the similar data in clusters, and finally perform the data split based on clusters. So the first step is evaluate the similarity. So how we can see if two geometric cases are similar or not. A comparison of the geometric case will be performed through a metric that will indicate the degree of similarity of geometric case. The comparison metric has to be symmetrical, so that for any geometric case A and B, the metric of case A with B will be the same as the case B with the case A. To facilitate the explanation, I create an example with 5 cases of plates. We can see that they are similar. Someone is more similar than others. So the question now, how I can say if, for example, the case 1 is more similar or not with the case 2 comparing with the reference case that is the case 0. For that, we need to create and use some metrics, and this case, case 0 will be our reference. 1 and 2 will try to evaluating the variation of the radius of the hole, and the case 3 and 4 will evaluating vertical and horizontal translations respectively in relation to the case 0. And finally, the case 5 will also allow evaluating rotations in relation to case 0. The metric used to compare all the geometric case is the Euclidean norm of symmetrical mean absolute percentage error of mechanical properties, namely moments of inertia, x and y, and centroid. So these two is like moments of inertia, depends of our geometric case, and the last two ones is about the position of the center of the geometric case. And here we have the equation for this parameter for a given variable. So for example, here here variable a and variable b are the value of the variable understanding in the geometric case A and B respectively. So for example, here we can see that we have need to calculate for SMAPI. So for example, for Ex, we will calculate for the geometric case A, B, and after we do the equation, and we have the first one, and do that for the three last ones. A comparison of geometric case will be performed through this method that we are see in this equation, and after that we do that for all the case, we can create a matrix. And here, if you can see on this matrix, for example, for case 0, we can see that the case 4 and 5 have the value that is not so big. So the case 4 and 5 are more similar with case 0 than, for example, if we compare with case 3. And if we look to the picture, we can see that. So case 4 and 5 are much more similar with case 0 than, for example, case 3. So the metric is like, if it's bigger, it's because the cases are not similar. And with that, we can put on a matrix like that. More things. I don't know if someone has some question at this moment. Okay, I will continue if someone just please ask. Okay, after calculate this parameter for all the geometric case, the clustering of the geometric case is performed through a graph. So we will convert this information in a graph. The graph is constructed based on the comparison matrix. Here, the nodes correspond to the geometric case, and the links are defined taking into account the value of the comparison matrix. So if the comparison matrix between two geometric cases is equally or less than a value that we define, then there is a link between these two geometric cases in the graph. Otherwise, it don't exist signs that the comparison metric is very high. Translation into very different geometric cases. So the idea is like, if the geometric cases are similar, we keep the link between the two geometric cases. If they are not similar, we don't put the link between these two geometric cases. For example, if the value that we defined to be similar or not was 100%, of course, in that case, all the links will be kept and we don't remove any link. If the parameter is 0, is because we don't have any similar case. So in that case, we don't have any link. As we decrease the parameter, of course, the number of the links decrease because we are more rigorous, so we don't have any so many similar cases, and the number of the clusters will increase since we are increasing the degree of the restrictions of the connections of the nodes. After the graph was building, we apply this method to create the clusters of the graph. What is the clusters of the graph? The idea is simple. We just create groups with the cases that are more similar. For example, here I put a picture from 3 clusters. And if we look for example, for the cluster 2, we can see that the holes that are all the geometric cases that have the smaller holes. And for example, if we look for cluster 3, we can see that these holes are bigger, and even the configuration of those are very similar. So the idea is try to put the different geometric cases in groups and try to do that with the geometric information. After that, taking into account the clusters, that data set is defined never using the same cluster for training and test data. The goal is to assign the geometric case of the largest cluster as training data, and then the rest clusters as test data. After that, the training data set will divide into training and validation data set. Here we have all the information for the test data, training data, and validation data. Now, I will speak about the model, in this case, MLP. The MLP model is sequential and point-wise prediction the von Mises structure for a given point in the domain and for a given geometric configuration. So the inputs are an array of shape 1 by 2, because we have only 2 coordinates, is two decays. And the second input is regard to the geometry. So in this case, we have 6 holes. So the other input have a shape 6 by 3. 3 because we have like 2 components for the center of the hole and 1 for the radius of the hole. The construction of the MLP model is performed using the sequential model. We treat the 2 inputs differently. The geometry is concatenated into the coordinates of the point. The input to the main short-to-speak neural net whose output is the von Mises stress. The last layer output is a single continuous value. The number of hidden units in the layers and the number of the layers were considered as hyperparameters and appropriately analyzed. The study of these hyperparameters indicated that the model used in MLP for the plate with 6 holes and 11 layers hidden with 512 neurons each. On this table, we can see the best model for the study of the hyperparameters. And in all layers, with the exception of the last one that presents a linear function, the activation function is a ReLU. The optimizer chosen is the Adam, and the evaluation metrics are the minimum absolute error, MAE, and the mean square error, MSE. MSE was chosen for the loss function. The model was trained for 400 epochs with a batch size of 5,000. Here we can see this figure show the learning and the validation curves for the MLP model, and we can see that the learning and the validation loss curves decrease as the number of epochs increase.
Okay, Bruno, again, just to internalize this a little bit better, because I think this is the magic of the network, okay, right? Doing something. Okay. So, just wanted to appreciate again the von Mises stress that you're evaluating. That you're evaluating at each node, correct? So you have 1,000 nodes, 10,000 nodes. The more fine-grained, the better, I suppose. That evaluation is happening because the network was trained to do so, correct? It was trained to do so. So just wanted to clarify 1 or 2 things. When I looked up von Mises stress, it wasn't a PDE, unless I'm confused about partial differential equations. Is that equation is that the equation that you're solving, that von Mess equation with sigma equals blah blah blah? Is that the equation that is being replaced by the network training? So there's
okay, I understand your question, but I'm not sure with about the equation are you talking about? Sorry.
Oh, I don't know. I just did a Google search for von Mess and it showed me an equation. But is there an equation that is a partial differential equation that yields a stress number? And is that I just want to clarify that when I do my research. Is that what this network is replacing through a prediction?
Yeah, of course.
Okay.
To calculate the von Mises stress, you don't need like you have equations, and even for this case, is a simple case. You have like all the equations for the plate with the holes, so you can do that like analytically. Here, the idea, we are of course not implementing FEM because we need the data to train our model. But the idea is like, okay, if you went for other plate, we don't need to do that analytically with the equations. We just give the inputs. In that case.
And any shape, I mean, it could be a triangle, a rectangle, any shape you can push through here.
Okay, nice question. You are speaking about the shape of the holes or the shape of the plate?
Well, you're smarter than me, so I'll say both. Yeah.
Okay. I think for the shapes of the holes will be more easier. So if you give a different shape that we don't train, I think the results will be okay and accepted. If you change a lot the shape of the plate, maybe the results could not be so good. Depends of how huge or easy your data set. Makes sense?
Yeah, thank you so much.
Okay, perfect. Okay. To finalize the MLP, here we have some figures that represent our results for the plate with 6 holes. Here the results obtained by MLP are present and compare with the results obtained by FEM. This comparison is performed using the absolute error. In addition to the visualization comparison, the MSE and the MIE were measured for all points on the plate and for points located in the regions around the holes. This region contains all points located at a distance equally or less than 1.5 the hole radius. As we can see, the MSC and the ME metrics are higher for all cases in the region around the holes, and makes sense because since it's these regions that we have the stress concentration factors, so it's normal that the error will be bigger there, and this concentration of the stress make the model more difficult to predict the stress at this point. But despite this, the metrics present good results, even when compared to the metrics obtained for the entire plate. The last table that we have here shows the average values of MSE and ME for all points on the plate and for points located in the regions around the holes for the 37 test case. Okay, so with this presentation, we pretend to focus more on MLP and try to give all the steps for the first machine learning technique. Now I will only present some results and try to be more fast about the next two ML machine learning models. So the next one will be convolutional neural networks. Here, our neural net have like encoder and decoder structure, such that the input is a regular mesh describing the geometry, and the output is also an array containing the von Mises stress distribution. Now, here we have the results in the test data set are these with a loss of almost 3,400. The last one, we will talk about graph neural networks. And here, our research now is more focused on using graph neural networks. So I will give a short describe about what is a graph neural network. A graph neural network can be represented by a G and is defined by a set of nodes, X, and a set of edge, E. A graph structural nodes, edge, and their properties is usually represented by a matrix adjacence. These matrices that contain the information about each node of the graphs and connected, and the node features matrix with the features of each node. Note that N is the number of the nodes and in the graph, and F is the number of the features. The left figure that we have here show the links between the nodes of the graph. Blue square means that the node row ID is linked to the node column ID. For example, if we look for this picture, we can see that node 0 is connected to node 1, and the same node 0 is connected to node 9. If we look for our figure, you can see that that is true. The node 0 is connected to node 1, and the node 0 is connected to node 9. One thing that I want to say, like, for example, node 0 is connected to node 1, but node 1 is connected to node 02. And if we go here, you can see that we have this square 2, and we can see that the node 1 here is connected to node 02. So this matrix will be every time symmetric if we have this type of connection that the same nodes are connected to each other. Now here we can see some figures that is the preliminary results using graph neural networks. And I think for these pictures we have 30 messaging passing, and we see that the results are very good. And if you look for the error is less than the error that we have for the MLP. So about the conclusions that I want to say, SimuStruct is a 2D dataset with numerical simulations for many boundary and long loading conditions, different materials, and varying refinement levels. SimuStruct contains the geometrical model, the mesh for varying levels of refinement, and the structural simulations. SimuStruct includes the class case, plate with the holes. SimuStruct will provide training and evaluation data for MEL-based methods, enabling optical mechanical design solutions. How we see MLP, CNN, and GNN implementations are able to correctly predict the von Mises tracks. This shows the potential of SimuStruct to train and test machine learning models in the area of structural mechanics. Considering the evaluation of machine learning tools and possibly applications in mechanical design, these datasets are fundamental pieces to develop design tools that can provide optimal solutions in near real time, enable better and faster product development. And thank you for...
Hey, Bruno, one last question from me.
Okay.
Again, if maybe I misunderstood the training process, but can I use images of like a pressure heat map instead of the pressure points? Like, can I just use the CNN to do something similar? So the input would be the plate and the holes, and the output would be the heat map, the heat map itself as an image. And then if I present it with another kind of plate with different holes, would it be able to generate a heat map with that image? Is that sort of a plausible approach as well?
Okay, yes, but you are speaking about can you repeat again? What is the application that you want to do?
No, so in what you have here, and maybe I'm a little bit behind in terms of how CNN works, but here you have a plain mesh, like the mesh, and then you have a picture, literally a picture, an image with a heat map, like it's blue on the top, and there's a gradient in terms of the pressure. Can I train a CNN based upon just these type of image for each of the different, data, like for a huge data set, right? So I have all these different plates and they have a corresponding heat map. Can I train that way as well?
Okay, but you are still like, you want to predict different things. You don't want to predict more von Mises, and you want to predict something with
well, I just want to predict the heat map as it looks like this visually.
Okay. Yeah, of course, if we have this information, I think you can use that for heat map too, you know.
Yeah, okay.
I don't know if someone has more questions about the presentation.
Really nice presentation, Bruno. Really appreciate it.
Thanks.
We can take a few questions, so we'll give the audience a couple of minutes. Otherwise, I'll give you back some time, unless you want to discuss something. Let's see in the chat. How is it with uncertainty, by the way? Did you take into account uncertainty? So when you have a result, by the way, and you have a specific megapascal value, would you be able to tell the range where it's actually accurate or inaccurate?
Okay. Can you repeat again, Joseph? Sorry, maybe I don't.
Yeah. Do you take into account? Do you take into account uncertainty of the results?
Sorry, I'm confused about your question.
Yeah, for example, maybe you've heard about Gaussian processes before. So once you get a result, it would actually calculate with a neural network the uncertainty band. So for example, if you have instead of having a specific scalar value of
yeah, at this moment we just predict we don't have like the value between two, you know. Only can predict for a specific value. Yeah.
Okay. How did you validate the method? Like, did you check it with experimental results as well?
No, at this moment we only validate with some FEM examples that we have, but we don't have like experimental real in the real world application. We don't have anything else. Maybe the next step could be to validate our results with that, but it's more difficult because we need some money to those tests, and it's not so easy.
How was it with the why did you decide for the graph neural networks in the first place? Like, it has pros and cons. Why did you go with the GNN approach?
About the GNN?
Yeah, exactly. Why did you choose that approach? Are there multiple ways to approach this problem, or does GNN have an advantage over other methods?
Okay, yes, we think so, because GNN, we have the information more structural. So, for example, and the other example, we see that for MLP, we need to have not a structural mesh. So we have, for example, if we have two different cases, maybe we have two different number of nodes. And that is a problem. With graphs, that is not a problem. We can have two graphs with two different number of nodes, and we can train the same model and make the predictions. So that is a thing that is good, because we don't care about the number of the nodes in our mesh.
Okay.
So yeah, so I think it is one of the advantage of the neural networks.
Okay, got it. Any other questions to Bruno? Otherwise, we'll have his brother tomorrow at the same time.
Yeah, at the same time.
Perfect. All right. If there are no more questions, thank you so much, Bruno. It was really, really insightful. And would you be able to share the slides with us as well, so that we can distribute them among the participants? Awesome.
Really
cool.
Thank you, Joseph.
Thank you so much. And I'll see you tomorrow, Joao, then. Same time.
Okay.
Take care, guys.
I see you tomorrow.
Bye-bye.
Bye-bye.
Thank you.